we're going to find the first partial derivatives of the function f of xyz is equal to xy squared e to the negative xz. Of course, these are partial derivatives because we have more than one input variable, and in this case we have 3. That means we need to consider the partial of f with respect to x, the partial of f with respect to y, and the partial of f with respect to z. If we want to be thorough, we would write down fx, xyz, fy, xyz, etc., but I wouldn't say that that's a requirement. Now we need to look at the function with respect to x, and it looks like with respect to x we have xy squared times e to the negative xz. Using then the product rule, we have u prime v, and so y squared e to the negative xz minus xy squared z e to the negative xz, because we're using the chain rule for that e to the negative xz. There's only one occurrence of y in the functions. There's no product rule or anything. So the partial with respect to y, 2xy e to the negative xz. And then likewise the partial with respect to z. The function itself has only one occurrence of z. And so we're looking at negative x squared y squared e to the negative xz. Those are our 3 first partial derivatives. And I hope you're seeing what I said in an earlier video, which was that you're kind of looking at this through a filter of kind of knowing which variables to ignore and which ones to pay attention to. Now, before we get into the next exercise, let's recall implicit differentiation in x and y. If we consider something like x squared y cubed plus 3xy to the 4th plus x squared is equal to 5. This is a great first semester calculus problem. To find y prime, or dy dx, we would consider basically y as a function of x. And so when we see x squared y cubed, we're going to treat that as a product, and we're going to use the product rule. And when we do, we're going to say we've got 2xy cubed plus x squared times 3y squared times y prime, where that y prime is coming out as the result of the chain rule because we're differentiating with respect to x and not y. For the next term, we have, again, a product rule. So 3xy to the 4th is going to differentiate to 3y to the 4th plus 12xy cubed times y prime. And then we finish off plus 2x is equal to 0. And our goal in a case like this would be to isolate y prime. By subtracting, factoring, and dividing, we would end up with y prime is equal to negative 2xy cubed plus 3y to the 4th plus 2x, all divided by 3x squared y squared plus 12xy cubed. It's worth noting that y prime is often written, even in this context, as dy dx. And so instead of writing y prime in those terms, we could write down dy dx for both of those, and it would mean the same thing. I'm bringing that up because we're about to use implicit differentiation on a multivariable function. And we're going to need to write it as partial of y with, or partial of z with respect to x, partial of z with respect to y. And so I wanted to bring back the Leibniz notation for what we're about to do, which is use implicit differentiation to find the partial of z with respect to x and the partial of z with respect to y for the equation x squared minus y squared plus z squared minus 2z is equal to 4. I need you to know these are going to be 2 separate processes. First, we're going to differentiate with respect to x. We'll get an answer. We're going to differentiate then the original equation with respect to y. We'll get an answer. We'll go first with respect to x. The derivative of x squared with respect to x is 2x. Y squared is a constant with respect to x, and so negative y squared, that goes to 0. Z squared is going to become plus 2z times the partial of z with respect to x. Likewise, negative 2z is going to be negative 2 times the partial of z with respect to x. On the right-hand side, the derivative of 4 is equal to 0. Subtracting, factoring, and dividing will give us the partial of z with respect to x is equal to negative 2x divided by 2z minus 2. If there are 2's everywhere, we need to reduce. And so we end up with the final answer here for the partial of z with respect to x of negative x over z minus 1. And it would be appropriate to write it as x over 1 minus z, incorporating the negative into the denominator, if you wanted to. Now what I'd like you to do is pause the video and find the partial of z with respect to y. Starting with the original equation here, the partial of x squared with respect to y is 0. Negative 2y is the partial of y squared with respect to y, and then we have plus 2z times the partial of z with respect to y minus 2 times the partial of z with respect to y is equal to 0. Here I can see that there are 2's everywhere, so I'm going to go ahead and divide those out now. And the partial of z with respect to y is then equal to y divided by z minus 1. I had to fix my curly little d down there. You know, I will tell you something about writing these things. I was teaching once and I was writing my partial of, say z with respect to y, and I was starting the stroke at the top and basically writing a 2 but cutting off the 2 so that it didn't have a little tail at the bottom there. And one of my students was like, that's confusing, it doesn't look right to me. And so what I do now is I'll start the stroke at the bottom, and it's less likely to look like a 2 if you start the stroke at the bottom. Just, word to the wise, make sure that what you're writing is legible to your reader.